Okay. Great. So what we're going to look at now is supervised learners, and how do we generally define the problem that we want to solve in machine learning. So the commonest way is to define first a loss function. So this is our loss function. And our loss function, it depends on a set of parameters to estimate, W. Okay? So here, what do we have? We have our training data. So this is, the observation xi. So this is one training sample I, and its corresponding observation or the target output yi. So yi is can be a label. It can be also a continued like a scalar value if we're doing regression. And what do we have here? We have an error. So this is an error function that takes in two things. It has two variables, okay? The ground truth observation that we have in the that we give. So this is the training target label or output, and we have the predicted output by the learner FW that we want to estimate for input xi, okay? So this is actually what we can call, sometimes we use this notation, the y hat, it's our estimation, okay? What our learner has predicted, the classifier has predicted, or regressor, or we can also use tilde, okay? And what we want to compute is just an error, a distance between our prediction and the ground truth basically observation. And we sum this across all samples. So this is why we have the sum right here. And we normalize, divide by the number of samples. Okay, so we can look at this problem as just, an error minimization problem, okay, or a loss minimization problem. So now we have an extra term right here. So this extra term, there is a reason for introducing that. So I'll give you just a hint, but we're going to look at this term later on in much more detail. But for today, this term is actually called a regularization term. And the first one, it has a name too. So this one we call it generally fidelity to data term. So how truthful or close our prediction is to the real ground truth data, okay? How good it fits our observations. Now, the regularization term tries to do two things. So basically here, what we have, imagine in this case, if you guys remember last time, we had, if we want to minimize the error and we want our model to make no mistakes at all, then we will end up with this case, which is overfitting, right? Because we want to exactly follow the boundary between these two sets. So we are not allowed to make any mistakes. So in this case, it is good that we're not making mistakes, but there is a big problem, and the first problem is generalizability. So when we add new samples, because the boundary is very constricted to the training, right? It's not flexible. So, and also, we notice that in this case, the boundary is quite complex, right? It has a complex shape, okay? Now, in the other case, in the good case, we want to relax this constraint. So we smooth the boundary. We allow the model to learn a more simple representation, okay? Or a more simple mapping function f from the input to the target space. So in this case, we say that we have regularized, yes?
Is overfitting always bad?
Overfitting, yes, it is always bad because it cannot generalize. Yeah, you can actually try that. Yeah, so by controlling the parameters of your learner, you can overfit it to the training data and see how it performs on different different independent testing sets. Okay. Yeah, so this is, in this case we have regularized the learner. So the regularization term, it will somehow allow you, it controls the complexity of the model. And we added it, or the learner, okay? Plus, it tries to avoid overfitting. So this is the role of the regularization term. Now, what we are interested in studying for today, just in a simple way, is this problem. We want to learn how to minimize the loss function, and the loss function depends on what? It has only here a set of variables, or a vector. Can be also matrix, can be so many things. But in this simple case, let's say it's a vector. So it's a set of parameters. W1 to Wn, for example. Okay? So if we find the optimal W, then our loss will be very minimal. Okay? And in that case, we have solved the problem because our learner is very well trained, because its predictions are very close to the target outputs. Okay. So here, this is just a summary too. So what we have, we want to minimize this, and here are the different definitions for your for the loss. We have the learner. It has a set of parameters W, and what we want to minimize is the loss function. So this is just a brief summary. And the mapping, we're learning from our input samples xi to yi. Now, I would like you guys to look at this, okay? And tell me if let's hypothesize that this is, how our loss function looks like. And this is a very simple case. It's one-dimensional case. So L depends on a scalar W. But in a high-dimensional case, believe me, it's so hard to visualize your loss function. You won't even know how it looks like. You didn't know where, its shape, what shape it takes. It's very complex. You can't see it. But calculus, which is magical, can help us see the function, can help us, imagine the geometry of the shape of the loss function or curve. How do we do that? So here, in this case, what are we looking for? If we want to minimize our loss function, what are we looking for? WK. So we're looking for the minimum, okay? So we're looking for a global minimum right here. So we want to find the WK. This is what we want our optimizer to estimate. Because if we find the WK, our loss function has the minimum value. We solve the problem, okay? Now, how to find what we're looking for? How to find this minimum? Take the derivative, okay? So this is what we call the tangent, and I guess all of you guys know that in calculus. So if we compute the derivative of the first derivative, okay? So let's say maybe this is not the right way, but yeah, so the derivative L prime of W0 at different points, and we notice that if we have a minimum, then our derivative is equal to what, guys? 0, right? So we have, the slope is 0, okay? So we have a flat line. So we're looking for that. Now, this is, exactly what you guys said. So how calculus can help us read the geometry of a function at different points. And this is amazing because I can give you numbers. I can tell you my loss function at W equals to 155. It has a slope of 0.5, and you can imagine it in your head without even looking at the curve, okay? So here we will talk about two things. First, local linear approximation of the function at a specific point V, okay? And also nonlinear approximation. And the first derivative is actually the linear, first order, most simple approximation of our function in that around that point, okay? So here we have what we call so we have the tangent, and in this case, this is, the first derivative. But we also have, what we're going to see, we have also the second derivative, which tells us about the curvature around that point, okay, around that our observation or current point V. Now let's look at a very simple case. Now in this case, what we have, we're going to look at the univariate function L, which means it has one variable, and we will look at the first order and the second order, what we call Taylor approximation. This is, I know most of you guys probably know this, but this is a good reminder. So here, a linear approximation of this function, what we define a new function. Let me just zoom a little bit. Okay, so we define a new function h of w, okay, around the point V. So this function, this local approximation, is only valid if we are within a local neighborhood of our point, and it does not. Basically, this assumption doesn't hold if we go far away. Okay, so it's a local approximation. So we want to look at this, local behavior or geometry of our loss function. So this is, just a simple definition of the gradient. And what you guys notice, it's linear in omega. So this function has two important properties. The first one, if you compute h of v at our observation points, we get L of v, okay? So it has exactly the same value, and the derivative also is exactly the same. Okay, so I guess all of you know how to compute this. So if we replace w by v, this term will become 0, right? So we end up having L of v. And the derivative, for the derivative, you need to keep in mind that we are computing the derivative with respect to omega, so the v is a constant, okay? And then we evaluate it at v, okay? So in this case, you can see that nicely this h function has exactly the same slope and the same value at b. That's why we call it first order linear approximation. Now let's look at the second case, which is the second order. And in the second order, we're approximating basically the curvature of the function. So this is, our function h of w. This is the first order approximation, and we're adding a second order approximation that integrates or takes into account the second derivative of our loss measured at the point V. Okay, so guys, I will give you just a 1 minute, and I would like you to compute this. Just, even if you know what these quantities are, right, I would like you to derive the maths, okay? Just rederive it. So we know that h is a second order approximation of our loss function L at around point or observation V. So what you need to do is, the first one is quite easy. So you're just replacing the W here is your variable. You're replacing it with V. So the first one should be quite straightforward. So we have L of V. So you derive first with respect to omega, and then you make the measurement or the evaluation at point V. Okay, you guys got that? Right, because these, I replace the W with V, so these terms cancel out, and that's how we get the first derivative. Is anyone confused? I can walk you through that. So basically, let me do it again. So h prime of omega, we are deriving with respect, omega, or sometimes we call it omega with W, okay? So h prime of W is the derivative of h with respect to W. So the first term here, it's constant. Deriving for a constant with respect to x. So, but here I just replaced the casual x in calculus with W, right? It's 0. So that's a 0, right? Now the second one, this is a constant times my variable minus L prime of V. So that's a constant, L prime of VV, that doesn't depend on W, so that's a 0. So then I keep the constant, okay? So the derivative of 2x with respect to x is just is 2, right? Okay. So that's what we and then the next here I expanded the squared norm, and then you perform derivation for each term independently. This is a constant in W, so we keep constants, but then the derivation of W squared is just 2W, and that's how we keep doing this. And then if we derive this now, okay, if we derive this with respect to again W, so to get the second derivative, you're gonna see it gets expanded, and then when we evaluate it at V, it has exactly the same curvature. Okay, so you guys can derive this manually. Great. Now this is in 1D. Have you guys seen high dimensional space? What happens? The gradient and the Hessian. So now we're generalizing this, concept to a high dimensional space where we have our loss function. It depends on many variables. So the casual case is just, a scalar, but in this here what we have our W belonging to Rn. So Rn times 1 is just a vector, okay? So the local approximation function, the first order approximation function h of W, it's just the same formula, except that we are replacing the first derivative with the gradient vector. Okay, so in this case everything turns out to be vectors or matrices because we're not operating on points anymore. Okay, so our the gradient of partial derivatives of our function, and here we evaluate it at the point V, is just a vector. So the first element is just the partial derivative of our loss with respect to the first variable or the first direction. Okay, so we're looking at how much our loss changes along the first direction around that point. Okay, and then we look at its slope along the second direction. So, but we have n directions, right? So that's what we do. We compute the partial derivatives with respect to all directions. Okay, so let's say we have a function. Let me give you an example to see if you guys understand this. So let's say we have our function L of a vector omega 1, omega 2. So this is my vector omega, or W. I should keep saying okay, so if I trip and say omega, know that it's W, right? Because sometimes we use both. Okay, so here let's define it this way. So we have 2 and 1. Okay, this is just element-wise product of just 2 vectors plus let's do something like this. Okay, so this is the dot product. So this is, WT, W transpose, okay? So in this case, what we have, if we expand it, so we have just, this is the regular element-wise multiplication plus, and we have omega squared Right. Okay. So now what I would like you to do, guys, is compute the gradient of L. So this is the gradient. So we have the gradient with respect to the first variable and the gradient with respect to the second direction, okay, or second variable. And let's write it down. Okay, so the first one, when we are deriving with respect to W1, W2 is considered as a constant. Okay, so here, if we derive this one, it's 2 plus 0 plus 2W1 plus 0. Okay, simple. And then the second one is same thing. So we have like the first one is a constant, so 0 plus, this is, just a constant now, 1 plus, we have 0 and plus, good. That's it, that's our gradient. And then if we want to evaluate it, you just plug in the values, okay? At one point, if you want to evaluate it, so let's look at this. So I know I've given you a very simple example, but 2 plus 2 omega 1, and then we have 1 plus 2 omega 2, or W2, come on, okay, it's all right. And then you can evaluate it at L, maybe, I don't know, 1, 1, and see what happens. So it's so easy. So you're just replacing your W's with these values. So this is 4, and this is 3. Now you guys get it. Now it's so easy to generalize to the Hessian because you know how to do this, okay? Now in the second order approximation of our function h of omega, we have exactly the same, the first order plus the second order. So the second order, what does it remind you of, guys? So this is just like it reminds you of the Mahalanobis distance, right? But, right, so it's like, exactly what we saw before. If I scroll back up, so you guys, you will see. And this is, we had our sigma, the inverse of the covariance matrix. Now we're replacing it with the Hessian matrix, okay? So this is a quadratic form. A second order derivative, but in this case it's a second order derivative of our loss function. So how do we define the this term right here, which is the most important one? So this is what we call the Hessian matrix, and if our variable omega has n dimensions, then the Hessian matrix will be it's a n by n matrix, okay? The way we define it is so simple. So we're computing the first, so let's say this is, the Hessian matrix, and in a big example, this is the ith row, jth column, and we have an element right here. What is this element in our matrix? It's just the derivative of our function, okay? First, we derive with respect to the variable or direction I, and then we derive with respect to the direction j, and we have like, two consecutive partial derivations, okay? So quite simple, and this is how we do it. So you guys can look at the previous example, or maybe there are many examples. Actually, this chapter is taken from, it's chapter 2 in the book Machine Learning Refined. So please have a look at, you can read the whole chapter, and there are a few exercises that you can solve to just, if you want to refresh your memory with regard to calculus, okay? So our Hessian matrix tells us about how our function looks like, but how can we know that? So here, well, this is a simple example that let's look at back at this example. So go back to the first order. So this is, for example, we have our W1 and W2, and here this is our L of W, and W is the whole, it's a vector, right? in this case. So this is how our function hypothetically looks like, our loss function, for example. And here what you need to do is like I've shown you, so you guys just plug things in. So this is, you know, if we want to measure it at 5, 2, so we just put the value. So this is, you know, our point or our vector. And here we have the derivative. So we just compute the first derivative of our loss function and evaluate it at v. So here you can just, you know, write down the derivative of L, but, you know, put v, and then because we don't know what L looks like or what is the exact formula in this case, but this is the general form, okay? And transpose, this is important because first we had a vertical vector, now we're transposing it, and this is a dot product, so now it's times W minus V. So W minus V, just, you know, W1 minus 5 and W2 minus 2, okay, in this case, because this is our point where we're making the measurement or the local approximation. Now, very important question. H of W belongs to what? What is this? You should know this, right? What is that, guys? Is it a vector? Is it a matrix? Is it a scalar?
Scalar.
It's a scalar. Yes, it's a scalar. It belongs to R, right? We're measuring a single value, right, of two variables, of you know, two variables here. Like our point has two variables, omega 1 and omega 2. This is why we have a dot product, and you can see this is, you know, this belongs to R, and that's why we're transposing, because we're having a dot product between two vectors. So this belongs to R2, and same applies for the second order. Same thing. So you guys can plug this in very easily. So it should not be difficult, but you can write, you know, the Hessian matrix of our loss function. And here I'm just going to write it down for you. So it should be, we have omega 1, or, okay, omega 1, omega 2, omega 1, 1, sorry. And we have 1, and then, sorry, 2, because this is row 2, okay, 1. And then we have 1, and then 2. And 2, okay? And then where are we evaluating this? At point V. And the rest should be easy because you guys, we've done first order. Okay, great. Now, there is one important question. So you guys said that to find the minimum, we need to identify the point where the gradient is equal to 0. So in one dimension, it means the slope is 0. But in when using a multivariate function, it means like the gradient takes 0 in every single point. So we have a 0 vector, okay? So your gradient here, it's a vector, right? So all those elements are equal, should be equal to 0. So you compute the partial derivative with respect to the first, you know, direction, second, nth direction, and then you're gonna have 0. Now, is this enough to find our minimum function? Do you guys think it's enough? So let's look at this. So this is exactly, you know, our gradient, how we're computing it along all directions, and it's taking 0. So this is our condition. This is what we want to solve. But let's look at this case. So you can see, what do you guys see here? We have many points where the gradient is equal to 0, right? So this is not enough to find the minimum point because we might end up having a maximum or a saddle point. So a saddle point is like, you know, when the curvature changes from positive to negative or negative to positive. So you have like, you can actually nicely fit two different curvatures to this point, okay? So what should we look for? What kind of information we can integrate, or what kind of constraint we can add to find the real minimum, like at least a minimum. We're not looking for global or local for now, but we're looking for at least a minimum, right? We don't want to maximize our loss. We want to minimize it. So looking at the geometry of this nice plot, this graph of our function, what else can we add in addition to the second derivative? So what does the second derivative tell us about the function?
It's concave or convex.
Yes, very good. So it's telling us whether it's concave or convex. So if we have a positive curvature, right? So it means it's facing upward. So this is, you know, a convex. So here our function is convex, right? So this is a minimum, but you can see if the curvature looks downward, right? So it's a negative curvature, then we have a maximum. And that's how we differentiate between maxima and minima in a function. Right, so here, let's look at this case. Okay, now it's blocked. Okay, cool. Right, so you can see, for example, if we compute the derivative of this function, so easy. I'm going to do it quickly. So this is, you know, 3w squared, and if we solve for 0, then we get equal 0, so which means, but still you can see it's a saddle point, right? It's not a minimum. Although we have solved for g prime of w. And then for the second one, what is the derivative for this function? Exponential of w. It's the same, right? So the minimum here actually is it's a limit. So when x and when w tends to minus infinity, the value of the gradient, it tends to 0, but it never really reaches it. Okay, so it's not really defined. Now in this case, what do we have? We have a parabola, and if we solve for 0, you can see we have w equals 0, and in this case we have a minimum, right? But it's not always the case. So what we need to add, we need to look at the curvature. So, right, so looking generally at, let's look at this example. So we're going to look at different examples. I'm going to get back to this one later on. But basically, when we have a convex function like this, that where the curvature is positive, then we know we have a minimum. And when we have a concave, you know, the function is locally concave, then it's not a minimum, it's a maximum. So our main condition, the second condition or the second order condition for optimality is having a positive second derivative, right? So we want our point that we're looking for, our optimum, to have a positive second derivative, which means our function is locally convex. So it's a minimum.